Oh, it's recording. Good. Okay, so yeah, let me first recall what we've been doing in the last few lectures. So we are dealing with algebraic number fields. So these are finite extensions to the number fields. These are finite extensions, field extensions of the field of rational numbers Q, right? And to this number field, we attached Dedekind zeta function. Dedekind attached the zeta function, which is a generalization of Riemann's zeta function. Right? It was defined, you remember, by this. So notation is that zeta k of S is equal to sum 1 over S I. The summation is over non-zero ideals to the power S, absolute value. But then there is an Euler product formula for this in the world of ideals and prime factorization of ideals, which is 1 minus 1 over S minus 1 over all primes. And of course, here, yes, I always write, I don't know why. That's terrible. Yeah, you mentioned that also last lecture. Yeah, that's awful. Sorry. Yeah, P. I say Euler product formula, but then I write sum. Yeah, that's, yeah. Okay, so this by definition is equal to, this is the order of the OK divided by I. So I is an ideal, non-zero ideal in the ring of integers of K. And I said this is a finite ring in general. And yeah, get that. Okay, so okay, ring of integers of K. Okay, of course. This is inside, yeah, right. Okay, now, so one thing that's known about it, this was already proved by Dedekind, is that this series is convergent and is holomorphic for real part of S bigger than 1. So zeta k of S is convergent. And holomorphic. The series for zeta k of S is convergent and holomorphic. It's not quite correct to write like this. If you write such a thing in a paper, the referee will cross this sentence and say, corrected. This is not the right way, because zeta k of S, when I say convergent, means that it is a series. But then when I say holomorphic, I mean it's a function itself. So you understand what I mean. And holomorphic in real part of S bigger than 1, right? Second of all, the thing is that it has analytic continuation. As analytic continuation. To C, take away 1 with a simple pole at 1. At S equal to 1. So this is exactly like Riemann zeta function. And so before continuing, let's look at some examples that we discussed. These are all recalls that I did not prove this, or I did not prove one or two either. None of them I proved. See, we proved it for Riemann zeta function, not for general. But we proved this in one interesting example, though I'll tell you what we did. So example 1 would be for k equal to q. I mean, this zeta q of S is Riemann zeta function. S of Riemann. That's one thing, right? And example 2, more interesting example, for k equal to qi, Gaussian rationals. Gaussian rationals. We computed zeta k. You remember there was a factorization. It was equal to product of two terms, two functions. I proved it in the last lecture. Yeah, it's really like Riemann zeta function, zeta S, times an L function S and chi. Well, yeah, chi is a Dirichlet character, is the only non-trivial Dirichlet character mod 4. Is the non-trivial Dirichlet character. So we touch with the stuff that we did at the beginning of the course. That's good. Chi is the non-trivial Dirichlet character mod 4. So in fact, we have a formula for this. L of S and chi is equal to 1 over 1 to the S minus 1 over 3 to the S, right? Plus 1 over 5 to the S. We proved that. Minus 1 over 7 to the S. So on and so forth, right? Now, this zeta is Riemann zeta, has analytic continuation to the whole complex plane, except c equal 1. And also it can be shown that this guy also has analytic continuation to the whole complex plane. And this one, actually, there are no poles here. This is holomorphic everywhere. That's because this character is non-trivial. That's the reason for this. But you don't see it now because this function is only convergent for real part of S. For what range of real part of S this function is convergent? But is this the maximum possible range? 0, yeah. Real part of S bigger than 0. This one. But now look at it. To show that, to prove that this has analytic continuation to all complex plane, in particular, there are no poles at 0 or other points. It's a non-trivial task, right? It's not obvious at all. Right? Yes, but initially, at least in real part of S bigger than 0, this is converged, and it's holomorphic. And by this result of convergence is just because of the results that we proved at the beginning. Because on the real line, real axis for S bigger positive, this is convergent by alternating series test and all that. Yeah. All right. So, but then we also computed the value of L at S equal to 1 in the last lecture, right? I mean, this L of 1 and chi, you remember what was the result of our computation? Which is 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9. You remember what was? It was pi over 4. Okay, so if you put this and that together, what can you say about residue of zeta k at s equal to 1? So now what is the question is, what is residue of zeta k s at s equal to 1? What can you say about its residue? Residue of zeta. Exactly. Residue of zeta times pi over 4. Exactly, yeah. So this is holomorphic, nice, pi over 4. So we just have to know the residue of zeta at s equal to 1. And of course, we know the residue of zeta at s equal to 1. What is it? It's 1. Yeah. That's equal to 1. I'll tell you. 1 times pi over 4, which is pi over 4. Minus 1/2 is the value of zeta at 0. These are special values. Yeah, that's value of zeta. And the reason for residue of zeta at s equal to 1 to be 1, of course, is that we established that at least for real part of s positive, there is a expansion of the following form, right? We proved that zeta s is equal to 1 over s minus 1 plus phi of s, at least for real part of s bigger than 0. But phi is holomorphic. I proved it by integration by part. There was a trick. I mean, this is actually in Serre's book. It's a kind of a standard trick. So this, and this shows that there is a residue at s equal to 1, which is equal to 1. Okay? Good. So now, so we have two residues. One is residue of zeta k for k q, which is 1, and the other one is residue of zeta k for k equal to qi. So now the question is there a general formula that would compute the residue of zeta k for general field k? And the answer is that yes, there is a formula, and this is called the class number formula. So now let me just now recall. So this is now for any number field. So now in general, for any number field, residue of zeta k s at s equal to 1 is given by, so we have this, okay, so I write it again, that's okay. Residue of zeta k s at s equal to 1 is equal to, there is a formula. It's a, yeah, it's a fraction which is given by 2 to the r1, 2 pi to the r2, hk rk over wk root delta k. Okay, I guess last lecture I wrote 2r2, but that's the same. I'll just change the definition so that it becomes 2r. R2 is the same as 2r2 in my old notation. Is that what you wanted to say? Yeah, there's also. Yes, that's right. The discriminant. Yeah, exactly. There should be. Okay, so let's go through the formula. It's a very elaborate formula. So this formula was proved by, I mean, in the special case, due to Dirichlet for quadratic field extensions. I mean, Dirichlet actually never worked with quadratic fields in that sense. He worked with quadratic forms, but there's a language that you can translate between quadratic forms and quadratic fields. He, like Gauss, was concerned with classification of quadratic forms in two variables with integer coefficients, which is a big story. Like half of the in Gauss's book, Discourses Units Arithmetic, is about classification of quadratic forms. It also goes back to Lagrange, even Euler, and even Fermat. I mean, all these guys. Classification of quadratic forms. But then you can rephrase that in terms of quadratic fields and class numbers for quadratic fields. You can say that, yeah, Dirichlet did it, I don't know, around maybe 1830s, maybe 1840. But then the general case was done by Dedekind in this modern language. I don't know, maybe 1870s, 1880s, around that time, Dedekind did, when he was developing all these things. So, now, so R1 is number of real embeddings of K, and R2 is number of complex embeddings of K divided by 2. So it's half of complex embeddings because they come in pairs. So it's always an even number. You divide it by 2. And then HK is the important thing. I have to define it more carefully now. So HK is class number of K. So HK, by definition, is the order of the ideal class group of K. C of K. Well, C of K is the ideal class group of K. So that's a very important invariant you attach to any number field. Let me tell you how it is defined. It's a finite group. It's a finite abelian group always. And its size gives you the class number. And let me tell you how it is defined. So basically, this CK is quotient of two groups. One group is invertible fractional ideals. Of K divided by principal ideals. Principal ideals. So what is a fractional ideal? So ideal, of course, you know. So what is a fractional ideal? It's a generalization of the concept of ideal. So you can define it in different ways. For example, you can define it to be the quotient. I mean, you start with an ideal in OK, and you divide it by an integer in OK. So it's of the form 1 over, say, Ri, where I, subset of OK, is an ideal, honest to God ideal, as we know. And R belonging to OK is just an algebraic integer. An algebraic integer. Okay? Yeah. It's the same. That's another definition. Yeah. No, I was going to say that there's an alternative definition which tells you, I'll tell you what it is now. Yeah. So alternatively, question? Yeah. Because your hand, Nathan, goes like this. No, that's okay. I thought you were going to raise your hand. Sorry. No, that's fine. Yeah. Alternatively, a fractional ideal is a submodule J is inside K is an OK submodule module such that there exists R belonging to OK such that Rj is inside OK. Okay. Well, obviously, I can call this is an ideal, right? I can call this my I, and then I say that J is equal to 1 over Ri. So you see the two definitions are equal. Yeah. So yeah, this is a bit maybe abstract at first, but now, so these are fractional ideals. What about invertible? Okay, so we know that these ideals can be multiplied. There's a multiplication. So multiplication of even fractional ideals, you can do that. You know how to multiply ideals, but you use the same definition to multiply fractional ideals also, of fractional ideals. I mean, so J1, J2, by definition, is the set of all sums of xi, yi, where xi belongs to J1, and yi belongs to J2, and n arbitrary, any integer. So this is a product. Obviously, this product is associative and is commutative because the ring is commutative, right? The problem with this product is that there is no, and there is a unit here, right? So what is the unit of this? What is the unit for this product? Huh? It's okay. Yeah, it's just okay. And there is one issue though with this unit. What is that? I mean, what I'm saying is that it doesn't, not with unit, I mean with the product, it doesn't form a group yet. There's no inverse necessarily. So we are adding the condition of invertibility by hand. We just say that it's invertible if, yeah, so invertible. So J, a fractional ideal, is called invertible if there exists J prime such that JJ prime is equal to OK. And in that case, we call J prime in the inverse of J. So that defines a group, which is a huge group. I mean, yeah. Now, what are principal ideals? Well, principal ideals are principal ideals. We know those. And you take the quotient and you get this thing. Now, it is a non-trivial theorem that this is a finite group. It's a non-trivial result that is a finite group. So for those who know Riemann surface theory and a little bit of maybe algebraic geometry, but mostly just Riemann surface theory, this is an analog of, I mean, this invertible fractional ideals, they are analogs of line bundles, okay? So invertible fractional ideal, I mean, this is like analog of Picard group, invertible fractional ideal. Analogs of line bundles. And which correspond to divisors, more or less. Divisors on a Riemann surface. And these principal ideals, they're like principal divisors. They're divisors of meromorphic functions, right? So there is an analogy. I mean, these are not same because this is the world of number theory. The other one is world of Riemann surfaces. But there's an analogy between the two. That's one of the deepest analogies in mathematics. Principal ideals correspond to principal divisors. So these divisors are of the form f, where f is a meromorphic function on the Riemann surface. When you have a meromorphic function, you can take its poles and its zeros. You attach negative weight to poles and positive weight to zeros, and this gives you the divisor. But if you don't know the divisor, that's okay. We are not using it. Just for those who know it, I'm just giving that. There is a purely geometric picture behind this. This was not known to people. Then Dedekind and Weber discovered that there is this deep geometry behind it, and they made the analogy themselves. But before, so anyhow, so that's not. So RK now. So any questions, by the way, maybe before I move on? There is a lot to digest here. I agree. I mean, yeah. Yeah, CK is like a Picard group. Is this Gaussian? Yeah. Which in Riemann surface theory is called divisor class group. Okay, so if there are no questions, let me then move on with the definition. So HK, anyhow, is a quantity. It's not very easy to compute, but morally, for example, the following thing I believe is correct. HK is different from 1 if and only if unique factorization for elements in OK is missing. It's failing. Unique factorization fails in OK. Not for ideals. For ideals holds. For elements. Do you remember from your algebra courses where unique factorization failed in one of these number fields? So what are the elements? Yeah, so for what elements it fails? What is the factorization? Huh? 6 is equal to 2 times 3. So let me put it like I instead of that. I root 5. But where this story now is taking place, this story obviously taking place in Q of root minus 5. Root minus 5 adjoint. Now you can show that, well, 6 obviously is not a prime number in this field. So this is K. But 2 and 3 are prime. The same with these two. And they are not associate primes. They are not multiple of things with units of each other. So, because the units of these things are very easy to classify in this case. So this fails. Again, a little bit of historical fact. This is not the first example that mathematicians found where unique factorization fails. Do you know when they saw that the unique factorization failed? You wouldn't know. I don't expect you to know. So this example was given, I believe, by Dirichlet, most probably himself. But there is a dramatic example which was discovered by Kummer. Is Kummer with the umlaut? No, I don't think so. Maybe. I don't think there is. Anyhow, there's an example with, discovered by Kummer. So that's Q of cyclotomic field at prime 23. It fails here. Fails unique factorization. So the cyclotomic field, I mean, so what is zeta? What is C? I mean, 23. That's e to the power 2 pi I over 23. Well, 23 is, this is a primitive 23rd root of unity. It's a prime number. And you just look at the extension space. So the reason that Kummer came across this was that he was using this field and unique factorization in this field to prove Fermat's theorem. He saw a way of proving Fermat's theorem using unique factorization in cyclotomic field. So this is one of the first examples of applications of number fields to actual problems of arithmetic in Z. I think there was a question why we go to this crazy world. We don't understand Z. We have already many difficulties understanding Z. Why we are going to this more general world, which is even more complicated. Well, the thing is, sometimes over there, things become helpful to have that general picture, like going from real numbers to complex numbers. When you go to complex numbers, you have residue theorem, and you can compute real integrals that otherwise you couldn't, or it would be very difficult. So you're just going, extending things can have some positive, can be very, very helpful. So anyhow, so Kummer was assuming for himself that unique factorization fails in all, I mean, unique factorization holds in all these things. And then he calculated that this is the first example where actually it's not true. Maybe Kummer was aware of this. I think there was a French mathematician, Lamé, was assuming this, and he was giving a talk in French Academy, 1948, and he was boasting that he has a proof of Fermat's theorem. And then the letter of Kummer came, and there was a session. The Academy was in session, and then they read the letter of Kummer that said that it fails. So he was deflated. Poor Lamé. His case was killed completely. It's very dramatic, right? In the middle of a meeting, then there is this paper comes, oh, this is wrong. Yeah, very dramatic. Anyhow, so that's HK. Now, RK is the regulator. I won't define it, because in the two examples that we are doing, this is equal to 1. Regulator. It's called the regulator of K. It's a certain volume. I don't want to define it because it's 1. HK is also 1 in both examples that we are doing. Another thing that we need, the other two things are rather easier to define. WK is, what is WK? Is the order of roots of unity in K. Number of roots of unity. And this dk is the so-called discriminant, which I will define when I'm calculating it in the example that I have. Instead of giving a general definition, so I just define it for you. You'll see what the general idea is. I will define it later, yeah. Okay, so now let's verify then. So just for fun, I mean, nothing really difficult here. Just verify class number formula. Let's verify class number formula for the simplest number field, which is K equal to Q. I mean, this is completely boring, right? Well, first. Well, I mean, what is R1? R1 is the number of real embeddings of this, right? It's just one, right? I mean, 2R2 was the number of complex embeddings. There are no complex embeddings here. It's 0. And HQ is 1. Class number is 1. RQ is also 1. Right. What about WQ? The number of roots of unity in Q, there are two roots, 1 and -1, right? So it's 2. And the discriminant is, I can tell you, this is 1. I will, when I give the definition, you'll see that this is equal to 1. So what is class number formula telling us? Of course, and residue of zeta function, we know that, is 1, right? So now the question is it true that 1 is equal to 2 to the R1? 2 pi to the R2, huh? We had the formula, right? HK, so let me write it, HK RK divided by WK root absolute value of delta K. So this would be, well, R1 is 1, this is 2, this part is 0, this is 1 times 1 times 1, and then WK is 2, 1. So it looks like it's equal to 1. Yes, so this verifies, at least in this case. It's verified. Good. Yes.
So do these other quantities associated with
Yes, I believe they do, but I'm not 100% sure about that because, okay, so we have these analogies, but at the same time, it is known that these number fields are more complicated than Riemann surfaces. Yeah, because Riemann already did a lot with Riemann surfaces, but the progress in number field case, there are many questions that still we cannot. Well, there are many questions also we cannot answer about Riemann surfaces. That's true. But I'm not sure there is an analog of those, but there may be. That's an excellent question. Why don't you investigate this? What is the analog of discriminant in this case? Or yeah, I mean, any of those.
the regulators?
Yeah. That's an excellent idea to check. All right, so now let's look at the next case, which is hopefully more interesting and definitely is more interesting. So the case of k equal to zeta q as qi. I mean, k equal to qi. And in that case, we saw that zeta k s is equal to Riemann zeta function times this particular Dirichlet L series, and we computed the residue of this. That's equal to pi over 4. Now, in this case, R1, how many real embeddings this guy has? None, because it's a complex field, so it has no real embeddings. But what about R2? Is the number of complex embeddings divided by 2. There are 2 complex embeddings, right? A plus IB, A minus IB, the standard one and the conjugate. So this is also 1. Now, HK is equal to 1 because unique factorization holds in QI. It's a PID. OK is a PID, so unique factorization holds. So HK is equal to 1. And I don't calculate it, but I tell you this is also 1. We take it in good faith. Yeah. Sorry, my notation in last lecture was different. I used 2R2, so yeah, that's the kind of. But then I had to, sorry, I'm confused about this. Yeah. So now, what about WK? There's a number of roots of unity in OK. There are 4 of them, right? 1. No, I is not. Is I a root of unity? No. Oh, any root. Yeah, that's right. yeah. So it's 4. I'm willing to bet it's 4. Yeah. Okay, good. It's 4. Now the question is, what is delta k? Now I can't escape now. I have to give a definition of delta k. So what is delta k? Delta k is actually a determinant. So let me write it like this. It's determinant of sigma 1 b1, sigma 1 b2, sigma 1 bn, and then there is sigma 2 b1, sigma 2 b2, sigma 2 bn, and you just compute, and then you get sigma n b1, sigma n b2, and then sigma n bn, and then we have to square it. So let me tell you what these guys are. I mean, so now in general it can be shown. I mean, that's what you have to take a course in algebraic number theory to see these things proved. So it's not analytic number theory, but we have to know it anyhow. In algebraic number theory, they show that actually this OK is a lattice inside K. In what sense? So OK is a lattice in K. So in other words, there is a basis, there's an integral basis, okay? So there exists integral basis B1, B2, Bn. So this is the basis inside OK. So in what sense it's a basis? Every element of OK, you can write it as integer linear coefficients, linear combinations of these things. Okay, so well, I mean, for any x belonging to OK, you can write x as sigma xi bi, xi belonging to integers. And actually, so this is even better than that. It's really basis for k over q. And bi, I from 1 to n, is a basis for k over q. So in other words, if you replace xi, if you replace these integers by rationals, you're going to get everything which is in k. Example? Well, the simplest example, of course, k equal to qi. I mean, in this case, you can take b1 equal to 1, right? And b2 equal to I. K what? No, that's my notation for k over q. It's not a quotient thing. It is true that q is a subfield of k, but I'm not quotienting. Yeah. Okay, well, let me just, this I said it when I was writing, I said it's over q. It's a kind of convention. But in this case, you see that this is true. Yeah, that's what you have. And now, what about sigma 1, sigma? So sigma 1, sigma 2, sigma n are complex embeddings of, are so I think they should be just embeddings. Yeah. Or embeddings, different embeddings of K in C. I mean, real embeddings also are acceptable in this case. So I'm not excluding them. Because if I do, then I'm going to say this doesn't hold for real quadratic fields, for example, which I know it's true. Yeah. Yeah, these are just embeddings of K in C. And then, well, what you do, you just take this complex numbers, you take its determinant and you square it. Yeah. Sorry. No, there are only two of them here. Oh. Yeah, this case, n is equal to 2 in this case. Yeah. B2. No, this is 2. That's 2. Yeah, sorry. Yeah, this is 2. Yeah. Mommy, if you add, for example, a root of a third degree equation, you need 3 elements. Nth degree irreducible equation, you need n elements, things like that. For cyclotomic fields, for example, this B1, B2, Bn's are 1, C, C2, C, up to C to the power n minus 1, for example. Yeah, there's a general pattern, that is a general theorem. Yeah. Any questions? The basis of? Is it obvious? No. This is not obvious at all. No, but it is independent. Yeah, it's discriminant. Yeah. It's not in. Yeah, the reason is that when you change basis, I mean, this is not very difficult. When you change basis, the relation between this basis and the new basis should be with respect with an element in GLN-Z, because it's an integral basis. So anything that's integrally expressible in terms of B1, B2, Bn should be expressible in terms of B1 prime, B2 prime, Bn prime. It means that the change of matrix, change of basis, is implemented by an integral matrix. GLN-Z, and determinant of a matrix which is in GLN-Z is plus minus 1. And if you square it, you get 1, and that's why you better square things. Otherwise, you would be it would be up to plus minus 1. Yeah. So that's the proof, more or less. Yeah. So that's not that was a good question. Any other questions? What?
What do we mean by?
Just embeddings. Field maps. Yeah. Which are isomorphisms, because in the world of fields, a homomorphism is an isomorphism. Not onto, but injected map. Homomorphisms are always injected. Yeah. So let me give you an example. For example, I mean, we did already an example, e.g. for Qi. Well, sigma 1, one of them is identity. Just takes to be identity. But sigma 2 of A plus IB is A minus IB. That's also an embedding. Oh, that's a different thing. That's just for complex ones. But here we are using all of them. WK? Which this one? Oh, that one was very easy. It should be on the thing. No, that's not difficult to see that there can't be any more because, yeah. Yeah, that's a fair question. I'll do it on the in the break. Yeah. Yeah, because you see, they have integer coefficients in OK, in OQI. You see, what points on the circle have integer coefficients? Just 4 of them, and that's it. That's the proof, actually. Yeah. Good. Any other questions? Yeah, it's good to ask questions. That's good. So in this case, yeah, 1 and I. Yeah, exactly. I mean, 1 and I. E1 is 1, E2 is I. And then we can compute the discriminant in this case. Let's see what it is then. What is the discriminant in this case? Question is that? In OK. In OK, yeah. Yeah, in OK. That's right. Yeah. Otherwise, you have to solve these Pythagorean, rational Pythagoreans, which are a lot of them. Yeah. Good. Any other comments or questions? Okay, good. Now let's compute this in using this information that we have here. So what is the discriminant then? I mean, the discriminant in this case is, so delta K is the square of the following determinant. So, I mean, this is just, the first one is just 1 and I, right? The second one is 1 minus I. And we have to square it. So we have to square minus I minus 2I squared. So what do we get? Minus 2I squared. I squared is minus 1. And we get minus 4, right? So square root of absolute value of delta K is 2. Okay, so now let's verify that the class number formula actually holds in this case. Just works at least. So the verification now here, maybe I just write here. Yes. Okay, so the left-hand side, which is the residue of zeta k s at s equal to 1, we computed this pi over 4. I mean, for Qi, of course, we are doing, right? We are doing for Qi now. They're very modest, very modest. This is a very, for Qi. So this we calculated. Now, what about the right-hand side? Is 2 to the R1. So what is R1? R1 is 0. It's 2 to the 0. 2 pi. We have to raise it to R2, which is 1. Yeah, is 1. And then what else was in the HK, which is 1. RK, I told you, is also 1. You trust me in this regard. And then WK is 4. And what else? This one is 2. Okay, so this is pi over 4. So it checks. It's a fantastic formula. Again, one can ask, what is the analog of this in Riemann surface theory? Because there are analogs of Riemann rock in this case. This has been proved by, actually, the first version was proved by Dedekind and Weber, and then they are crucial to study properties of number fields. But this particular one, I'm not sure if there's an analog. It would be good to know that, actually. Well, mathematicians' imaginations is very fertile. You don't underestimate that. Yeah. Yes. So maybe I just stop the video because we want to take a break, and then I'll answer your question. Hopefully this is